Okay, let's talk about the tutoring a little bit. So I'm pretty sure Kyla sent you guys an email about keeping the log, right? So you guys are doing that? Okay, so put as much as possible. I want to see your students' struggle or their work, the strategy they are using, and also I want to see your strategy, how you help them too. Okay, so put as much as possible in the log. And Kyla's gonna check on your log at least every other week. So I think she asked you to share your Google Doc, right?
I couldn't end up sharing it as a doc, so she told me just to email it to her every week.
Okay, okay, so either way it works, but you need to make sure you need to share that log with her, okay? Okay, then let's talk about probability. So last time we started probability and we talked about experimental probability and theoretical probability, right? So when we do a lot of experiment, we can make the theoretical probability out of that, right? So instead of doing just experiment for everything, we are using our probability, theoretical probability. And we also talked about how we can represent the outcomes, right? We can either use a drawing, tree diagram, or using the set. So here are the differences between experimental probability and theoretical probability. Very similar, whether you are actually doing the experiment or you thinking about, all the possible outcomes and favorable outcomes. Okay? For our case from now on, we're going to talk about theoretical probability. So even if we are saying we are tossing a coin, we are not actually tossing a coin, but we are using the theoretical probability for that, right? So probability of event is number of favorable outcomes over total number of possible outcomes. What do we call the total number of possible outcomes? Possible outcomes. What do we call possible outcomes or possible outcomes? We usually use S, big S. Sample space, yes, sample space, okay? So you need to think about number of favorable outcomes to the event over number of possible outcomes. For example, what's the probability tossing one coin and get head? Just head, right? And what's the sample space? Head or tail? 2, so 1 over 2, something like that. And we also talked about law of large number or the Nernst theorem. So if we do a lot of experiment, we're going to come very close to theoretical probability. Okay, and we also talked about we are doing equally likely outcomes, so fair coins or fair die, something like that. Okay. All right, so we talked about this here, like that is not there. Okay, last time I think we finished this one. You already have this in your notebooks. You do? Okay, so let's go over this a little bit. I mean, all of them together, okay? So the sample space is 1 through 25 all natural numbers. If a number is chosen at random, that is with the same chance of being drawn as all other numbers in the set. Okay, so nothing is unfair in that situation. Calculate each of the following probabilities. The event A, that an even number is drawn. So even number is drawn, how do we write the probability for that? We can have probability so for A, we are doing probability A that is an even number drawn, right? So we need to think about number of outcomes in favor of this event, right? So how many even numbers are there? 12. If you don't know how to, you can count to 2, 4, but it takes time, so you can go a little bit systematically. You can think about it starts from 2 as even number, 6, all the way to 24, right? And think about one-to-one corresponding relationship there. So 2 is from 2 times 1. 4 is 2 times 2. 3 is 2 times 3. 6 is 2 times 3, and so on. So you can see, oh, that's number 1, number 2, number 3, all the way. 2 times 1 makes 24. 2 times 12 does. So I can see that, oh, there are 12 numbers, right? So, okay, there are 12. And what's the sample space? The total number. 25, 1 through 25, so 25. That is the probability for even number. How about B? Probability of B event. B is the event that a number greater than 25 is drawn. There's no number greater than 25, right? So yeah, it is 0 because it's 0 over total number 25, and it's 0, right? How about C? Probability of event C that a number less than 26 is drawn. How many numbers are less than 26? All of them, right? So all 25 numbers are less than 26, and the total number is still 25, right? So what is the probability for C? 1. So pay attention to what we have here. Okay, let's look at D. D is a prime number is drawn. So probability D is the prime numbers are drawn. So let's look at prime numbers. So I'm gonna just list all the D, all the prime numbers in the sample space. So what is it? 2, 3, 5, 7, 11, 13, 17, 19, 23. That's all, right? So we can see 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. And sample space, total number is still 25. So that is it, right? How about E? The event E that a number both even and prime. The number has to be both even and prime. So we already listed all the prime numbers there. Which one is the even number? Only 2. So there's only one number out of total number, still 25. Okay? All right. So when you're looking at these numbers, what do you notice? Any probability, do you see any probability that is a negative number? No, right? Is there any probability greater than 1? No. What is the smallest probability that we can have? 0. When it doesn't happen at all, right? So that event doesn't happen. That event is 0. When do we get 1?
C is less than 26.
So this example, we got 1. So how can we generalize that? So greatest number is 1. How can we restate that in our own words? When can we have a probability of 1? The probability of an event is this is different from that one. Any event is 1. When? Our event happen to be same as the sample space, right? So it doesn't exceed 1, but it can go all the way up to 1. It cannot be less than 0, but it can be 0, right? So any probability is between 0 and 1, inclusive. So 0 and 1 are included. No probability can be negative number. So if you calculated any probability that is negative, or greater than 1, something went wrong. Right? So make sure your probability is always between 0 and 1 inclusive. Alright, so that's what it's saying here. So if an event is impossible, of course, there's no outcome, so the probability for that event should be 0. If that event certainly happens, it's 100%, right? That probability is 1. So I just talked about percentage there. We can also talk about probability in the percent, because it's between 0 and 1. If the probability is 0, it's 0%. If it's 1, it's 100% certain, right? So we can think about that. Any event A, and S is the sample space, then probability of A is always between 0 and 1 inclusive. So I put the diagram here. It's similar to the number line. We're talking about the probability. So if the probability is 0, the event is impossible. It's not going to happen at all. If it's 100% certain happen, then it's 1, right? Probability is 1 or 100%. If it's 1/2 or 50% of the probability, we can say, it can either likely happen or unlikely happen, half and half, right? So we can see that if the probability is in between 50% and 100% or 0.5 and 1, it's likely happen, but we cannot guarantee that because it's not 100%, right? But if the probability is between 0 and 1/2, it's unlikely happen. We cannot guarantee that it's not gonna happen. It can happen too, but it's unlikely happen. So we can interpret that number too, right? It kind of makes sense, doesn't it? So let's say today's chance of rain. Let me see what it is. It says 60% right now. So it's over here. It's more than 1/2 of chance of rain today. So it's more like likely rain today, right? And then it says in the afternoon, around noon until noon, it's 50%. So it's neither or, so maybe it's better to take the umbrella with you. But in the afternoon, after that, it says 20%. Would you carry your umbrella for 20%? I wouldn't either. Well, maybe it can happen. It can happen to have rain, but it's unlikely rain. So I wouldn't either. Okay, so we can interpret that too. All right. So here is a spinner divided into 10 equal parts. So sample space from 0 to 9. There are 10 numbers, right? From 0 to 9. Event A is spinning a number in the set 0, 1, 2, 3, 4. So what is the probability of A? Everybody. What's the probability of A? 5 over 10, which is 1/2. 5 over 10 or 1/2. Event B is spinning a number in the set 5 and 7. 5 and 7. So what's the probability of B?
2 over 10.
2 over 10. Or simplify that? 1/5, right? Okay, so we can do that. And let me ask you a question. What is probability of A union B? Does anybody remember about union? Union is event A or event B. So it can be event A or it can be event B. So if I spin and got number 1, it is A or B. If I got 5, it's also A or B. So think about A or B in this case. What's A or B? Can anybody talk about A or B?
Would you include all of the numbers so it would be 7 tenths? Is that what you're
Event A is spinning a number in the set of 0, 1, 2, 3, 4. Event B is spinning a number in the set of 5 and 7. So A or B is the getting number when you spin the number and get 0, 0, 1, 2, 3, 4, 5, or 7. Right? That's A or B. So how many numbers are there in A or B? 7 of them, 5, 6, 7, right? In this case, event A and B doesn't have any overlapping part. Is there any number that's an event A and B? No, 5 is not there, 7 is not there, 0 is not here, and so on and so on. So there's nothing overlapping. If you think about the from Math 137, there's nothing overlapping. So if I use my Venn diagram, event A and event B has no overlapping part, no intersection. So A has 0, 1, 2, 3, 4, B has 5 and 7. So nothing is in the intersection part. So when we are doing A union B, we see that, oh, that is 0, 1, 2, 3, 4, 5, and 7. I am putting all of these elements in set A and set B in the union. Why? Because there is no intersection. That's an empty set. When this happens, we call these two events as mutually exclusive. Mutually exclusive. They don't share anything. Okay, we call them mutually exclusive. If the two events are mutually exclusive, in this case, probability of A union B is the same as just count, probability A and get probability of B. You just add them together. But there's nothing, intersecting. So for our case, probability of A union B, by just putting A union B, we can find that is 7 over 10, right? That's same as. So you can count it that way, find the union of A and B first and find the probability for that. Or you can also think about, oh, there's nothing overlapping. So I know that's same as probability of A plus probability of B. So we already found the probability of A is 5/10 and probability B is 2/10. So yeah, that's same as 7/10. So either works. Later on, for most of the cases though, we're gonna have some overlapping part there. Then probability of A union B, you need to consider this part seriously. Because if you just add the probability of A and probability of B, what happens? You're counting this part twice because it's in A and also in B. So you need to take away probability of A intersection of B one time because we counted that twice. Does this make sense? We did this with a particular number of sets. So in Math 137, if you guys remember, number of elements in A union B can be counted as number of elements in A plus number of elements in B minus number of elements A and B, right? Because it is counted twice. This also works for these mutually exclusive one too. Why? Because this is 0, isn't it? So it's okay if you remember this one and apply this to any Venn diagram or any set. It works. Okay? Any question for that? Okay. So we're talking about mutually exclusive event here. The definition of a mutually exclusive event means there's nothing overlapping. So intersection is at the bottom. A intersection B is an empty set. Okay, that's mutually exclusive events. So I showed you the Venn diagram with no overlapping parts, they are separate. So mutually exclusive events. Okay, let's move on. Okay, so we still have the same thing here, right? Just talking about the same thing that I explained, right? You see that? Okay, so we'll just move on. Now, this is another really important concept, complementary event. Complementary event. So let me bring my whiteboard again. Let's think about one event in the sample space. So this is sample space. Now you can see the why we need a Venn diagram. Right? So this is a sample space, and let's say this is an event A. Okay? And what do we call the event that A will not occur? So outside of A, right? If you guys remember back then in the Venn diagram, how did we write this part? A complement, or we use that A C to complement. They are the same thing, okay? Some people like to have this notation, but some use that one. So if you see this or that, they are the same meaning, complement. So you can see that, oh, A complement means the event that A is not occurring, right? So let me ask you a question then. If probability of A is P, lowercase p, so probability of A event happening is P, what could be probability of A complement? Can anybody think about that? Oh, we can also use that as A complement that way. In probability, we use this notation more. What could that be? Probability of A complement. Let's think about that. If we have the sample space here and think about probability of the whole sample space, what is that? It's certainly happening, right? It's 100%. So it's gonna be 1. Say that again. If this whole thing happens, well, we're talking about every possible outcomes there, right? That's the event. So the probability should be 1, right? If probability of this part here is P, that plus outside part should be what? 1. So how can we find the complementary parts probability? We can take away, probability of A, which is 1 minus P, right? So you just need to remember that, oh, probability of an event and probability of a complement of that together should be always 1. Okay? So that's the relationship. Does it make sense? Okay. So that's what it's saying here. So let me show you my screen. So for example, event A is getting at least 5. When you roll a die just once. Okay, so at least 5 means what? Your number has to be less than 5. Oh, at least 5. Then 5 should be included there, right? So this is wrong. Oh, it says at least 5, so 5 is included, but at least 5 is 5 or more, so 5 or 6, right? So this is event A, right? And think about the complementary parts. So when you roll a die, you can have either 1, 2, 3, 4, 5, or 6. Our event A is 5 or 6. So complementary should be 1, 2, 3, 4. Right? Then you can think about sample space. Sample space is from when you roll a die, you have 1, 2, 3, 4, 5, and 6. So if you take away event A, the rest of them should be complementary part. But if you have complementary and event together, it should be same as the sample space, which is 100%. So if the event A's probability is P, the other part should be 100% minus that, or 1 minus probability of event A, right? Okay, so that's what it means. So let's actually calculate the probability of A. What's probability of A in this case? What's probability of getting at least 5 when rolling a die once? What's the probability of A? You can say 2 over 6, right? What's complementary event A's probability? 46. Yeah. If you simplify it, it's gonna be 1/3, and the other part should be 2/3. Okay, so together you always need to get 1. Okay. Right. So here are some relationship between probability of an event and the complement of that. So let me rewrite that for you and explain it. So we already know that probability of A plus probability of complement of A is 1. We can just play around using the algebra there. To find the probability of A, if you need to find the probability of A, think about that same as X. To solve for X, what would you do when you are added by a number? You can take it away, right? You can subtract probability of complement on both sides. Then what happens? This will be cancelled out, and you can have a probability of A is the same as 1 minus probability of complement of A, right? Same for probability of complement of A. So let me start with same statement. Probability of A plus probability of complement of A is 1. To solve for A complement, we can take it away because it's added by subtracting probability of A on both sides, right? Then this part is gone, and we have probability of A complement is 1 minus probability of A. And it makes sense too, intuitively, right? Because when you add these two together, it's 1. To get only one part, you can take away the other part. So that's what it's meaning here. Okay? I don't think anything's hard here. Okay, so let's look at actual problem here. Oh, no. Before we move on to that one, non-mutually exclusive event. So when there is an intersecting part, I already explained this, right? So you need to take intersecting part out to find the union. So let me ask you a question. Can you guys find probability of event E, probability of event T, probability of event E intersection of T, and probability of E union T? Find all four of them. I may randomly call out your name. That includes you guys in the online too. So you have this spin of the wheel with the sample space is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Event E is even numbers 0, 2, 4, 6, 8. Event T is triple, that's why T is a multiples of 3, so 0, 3, 6, 9. Then we can already see that intersection is 0 and 6. Then my question is, find the probability of each of these events and also consider the probability of E union T. Find all of that. Okay, so I wrote down the question here in green, and I am also asking you some questions in red. So maybe I want you guys to fill this in. So maybe I can call out your name now. Alyssa Leach. Alyssa Leach. What's the probability of the sample space?
So, 1.
Oh, very good. It's 13. Probability of E. Is it Madison Barnard? Madison Barnard, what's the probability of E?
5/9.
5/9. How many numbers are there?
Oh, I thought you're talking about E for 0,
Yeah.
2, 4,
Because of
6, 8.
Yeah, there are 1, 2, 3, 4, 5. So 5 is good. How about the total number?
9.
There is 0, 2. So if
10.
we have only 1 to 9, there are 9 numbers, but there's a 0, 2.
10.
There are actually 10 numbers. So 5, 10, or simplify
1
that.
1/2.
1/2. Thank you. And probability of T, Emily Gibson.
2/5.
Or 10.
4
Did you
tenths and then
simplify
2/5.
2/5. There we go. In E intersection T, how about Anna?
I don't know.
Probability of
that's-
E union intersection T. 2/10. There we go. If you simplify that, it's gonna be 1/5. Okay, now the hardest part. E union T. How did you find the E union T? Is there anybody who listed union of E and T? Raise your hand. Nobody did that way. Okay, then what? How did you find probability of E union T? Morgan, how did you find that?
Well, don't you have to find the ones that like overlap based off of the total and
Mhm.
subtract one? So, wait, overlap with regular E and T, not the union rate.
This is overlapping intersection.
Okay. So would you add like E plus T minus 2? Is that how you would do that?
So in probability, so you did a probability of E plus probability of T, then you take away intersection part. There we go. That's exactly what you need to do. It's very good. The probability of E already found it, 5/10. I'm gonna just keep it as 5/10, not the simplified form because everything else is 10. And probability of T is 4/10. And you take away intersection 2/10. So 5 plus 4 minus 2, 7/10. So that's one way. Very good. That's very good. If you want to list it, you can have the same result. So if you are listing E union T, let's see E union T. I see 0 is still the same. So we just write it once, right? So E union T means it's either in event E or event T. So or, so it can be in either. I see 2 is there, 3 is there, 4 is there, 6 is in both. You can just write it once, you don't have to rewrite it again and again. And 8 and 9. And I can count them. 1, 2, 3, 4, 5, 6, 7. So yes, probability of E union T is 7/10. You can check your answer that way here. Okay? If you have small number of elements like our events here in this example, you can list it like this. But if you have more than, more than this is so much more efficient. Okay, so remember, probability of E union T is union is you add each of that probability and take away the intersection part once, because it's overlap, we counted it twice, and we take that away once. It makes sense? Alright, so that's all about this, okay? So we're moving on. Okay, quiz. Be prepared. You guys need to fill up this part, okay? I will give you guys about 1 minute. 1 minute. So look at your slide there, yes? Get it all up. When you're looking at 4 and 5, you can use 5 for 4 as well, because the intersection part is 0 there, it still can be applied. Okay? It says any event that includes mutually exclusive events, but this is a special case out of all the any events. But you can also use the number here to there too. Okay? Slightly different, but you can still apply that. I'm pretty sure you guys are ready, right? Okay, Hana. Probability of an empty set, which means it's impossible events. This is 0, right? Okay, probability of S, all the sample space, but certainly happens. What's the probability for that? 1, right? So, let's start. For any event A, probability of that event is always greater than or equal to. What's the smallest number for the probability? 0, it's not going to happen, right? It certainly happened. 1, the number probability is always greater than or equal to 0 or less than or equal to 1, okay? Jalen, if A and B are mutually exclusive, so there's no overlapping part, what is union of those two events probability? You can just there's no overlapping part. So how would you find the union of these two events? You can separately find the probability of each event and then just add them, because there's no overlapping part, the intersection is 0. Okay? So you can just do probability of A plus probability of B. Normally, for any event, we do probability of A union B as probability of A plus probability of B, and you subtract the intersection part, right? So probability of A and B. But for this case, probability of A and B is 0. So you don't even have to take away 0. That's why we have only probability of A and B there. To make you guys understand that better, I'll write that down for you. To 4. It says A and B are mutually exclusive. A and B mutually exclusive. What does that mean? Event A and event B has no overlapping part, which means probability of A and B is an empty set. And what is the probability of A and B? It's 0. It's not gonna happen. There's no element in the intersection. So probability of A union B has to be union B is this, which means probability of A plus probability of B. This is a special case. But normally, for any case, we are saying that probability of A union B is probability of A plus probability of B. Then we are counting this part twice, right? So you are taking away probability of A and B, right? This works for this mutually exclusive cases too. Why? Because this is 0. For this case, there's no overlapping part. So probability of A and B is 0. So if we are taking away probability of A and B, it's the same as probability of A plus probability of B and take away 0 to it. It's same as just without it. Okay, that's why it works for this one, works for any event. It works for any event. Okay, so you need to remember that. Does it make sense? Okay, the last one here. If A is an event, then probability of A complement. Madison? A complement. How do you find the A complement probability?
Isn't it everything that's inside both S and A?
So to find the, if we draw a Venn diagram, you are right. So if we use the Venn diagram, so here is the sample space. In the Venn diagram, long time ago we used it as universal, but now we are doing only the sample space. So basically, they are the same thing. In the sample space, there's an event A. And my question is how we can find the probability of A complement.
It's 1 minus P complement
Of A,
of
you
A.
mean, right?
Yep.
There we go, very good. So probability of A, you can find that. To find the complement, you can just take that away from 1. Because when you add these two events together, it's gonna be 1. Okay? All right, so that's the summary of first section of chapter 9. So I'm pretty sure you can do all of this. Oh, we have time to do this. Okay, so let's do this together. A waffle contains 2 red teas, 4 blue teas, and 5 white teas. What is probability of the event or that is tea drawn at random is red? Let's just say that together. We already know how many reds there are. 2. Right? What's the sample space? 2 red, 4 blue, 5 white. So altogether, how many are there? 11? And 2, yeah. So probability of R should be 2 out of 11. 2 out of 11. What is the probability of the event not R? The complement of event R. If R is 211, not R should be 911. Okay, anyways. Okay, so we understand what that not means, it's a complement. What is the probability of the event that a T drawn at random is either R or blue? So that's union, right? So R union B. So that should be probability of R plus probability of B minus intersection part, right? So can we have, when we have drawn a T, it can be red and blue? You drew one out. It can be red and blue at the same time? No, it should be red or blue, right? So intersection here is 0, which means it's mutually exclusive, right? So we can just add probability of R and probability of B together there. What's the probability of R getting red? 2, 11. Probability of B, 4, 11. So together it should be 6, 11, right? Take away intersection probability to 0. So it's 6, 11. So that makes sense. Okay, the last one here. You can design a geometric model for the following experiment. I will show you the answer. Tossing a fair coin. To make it fair, you need to have 1/2 and 1/2 for each, right? So that's an example there. This is just one example. It doesn't have to be this shape, but geometric shape, you can have 1/2 of the probability for each. So it makes sense, doesn't it? The probability of getting head is 1/2, tail is also 1/2. Rolling a fair die, you can make, 6 equal parts. So like hexagonal shape, each one has 1/6 of the probability of fail. That's what it means. So I'm pretty sure you can finish the homework. What other homework do you have? 9.1? No quiz? I don't think so. Okay, just 9.1 is due Wednesday. Okay. All right, great job, guys.